Okay, folks, so I'm going to do some questions from 4.1 from WebAssign. Let me share that assignment here. So the first question was about problem 6, and I'm just going to copy down parts of the problem onto the whiteboard and then switch back to the whiteboard here. So question 6 asks, find the interval or intervals where the function is increasing and the intervals where it is decreasing. Enter your answers using interval notation. If the answer cannot be expressed as an interval, enter empty or null set. And then the function that they've given us is g of t equals 9t over t squared plus 25. Now, I know I've mentioned this in previous live sessions. You'll see on my screen that some of these quantities are highlighted red. That means that it's going to change for every user when they log in. So when you do this problem, again, this is problem 6 and 4.1, you might have a slightly different version of it. All right, so I will stop screen sharing and hopefully I am back on the whiteboard here. All right, so, so a couple general remarks about increasing and decreasing behavior. It's easy if we have the graph to identify if a function is increasing. It just means to say that it's increasing, that's going to go generally up as we go from left to right. There's an increasing function, and then a function that decreases goes down. And of course, we could have a function that does different things depending on what interval we are looking at. And actually, this purple one, just how I drew it, increases for a little bit right there and then decreases on the rest of the interval that I've drawn it. So there we go. So that's what we're talking about. That's like the non-technical summary of increasing, decreasing. Now, what you're not supposed to know is what this function looks like. Right? We're not supposed to graph it. You're not supposed to know just by looking at it what's going on. We are going to use the tools of derivatives to figure this out. And so the key understanding here is that g of t is increasing exactly when g prime is positive. Okay, so greater than 0. And g of t will be decreasing whenever g prime is negative. If g prime is 0, that means that's a point in the function where it's flattened out. Maybe it's at like a hilltop, right? Maybe we'll call that a local maximum in calculus, but like, yeah, a little crest in the graph, or maybe it's flattened out down there, or maybe some functions will flatten out briefly and then increase again, right? This could be something like that if the derivative is 0. And so really the whole chapter 4 is just about what can derivatives tell us about an underlying function. So what could g prime and maybe even g double prime tell us about the function g? So we're going to start this one by finding g prime. Now this function is a rational function, 9t divided by t squared plus 25. And so we're going to have to use the quotient rule to find g prime here. So g prime of t, using the quotient rule, is low d high. So t squared plus 25 times the derivative of the top, so times 9, minus high, so minus 9t, times the derivative of the lower function. So derivative of the lower function is 2t, all over the lower function squared. This looks like a mess of algebra, but it will get better. Okay, so we want to know when this is positive and when this is negative. Hold on just one sec. I just had a knock on the door. Let me just pause this for a sec. Sorry, guys, had a package delivery from UPS, needed a signature, so here we are back again. And so really what I want to do here is I want to find out when g prime is positive and when it's negative. And to do that, I'm going to find out where it equals 0. It's a continuous function, and so the only place it can change from being positive to negative would be when it crosses the x-axis. That is g prime here. So some other observations about this particular function. In the denominator, I have t squared plus 25. And one thing that's really important here is that that could never be 0, right? There's no number that we could plug in for t that would make the whole denominator 0, right? We can't make t, if t is negative 5, for example, and we square it, it becomes positive 25. So that's good news for us. I am going to simplify this a little bit. I know I said we don't have to simplify, but the numerator in its simplified form is actually going to be a little bit friendlier for us to work with. So we have t squared plus 25 squared. That can never equal 0, and so that won't give us any of the points where the function might switch between being positive and negative, or g prime might switch between being positive and negative. Okay, now I am going to multiply this out. So I have 9t squared, and then I have 25 times 9, that's 225. So 9t squared plus 225 minus, okay, well, let's see, 9t times 2t, so minus 18t squared. Okay, so I have a 9t squared and I have a minus 18t squared. I can combine those into just 225 minus 9t squared on top. I still have a t squared plus 25, the quantity squared on the bottom. All right, so we've already decided the denominator cannot switch signs. It's never going to be negative. So we don't have to worry about that. All we have to do anything there. The numerator might be able to equal 0, right? And if it can equal 0, that would be a point where maybe it's switching from being positive to negative or negative to positive. And if g prime switches from positive to negative, that's going to give us a boundary for increasing or decreasing behavior for its interval. Okay, now this is a special factored form here. It might be hard to see it, how it's written out, but if we think about where this came from, right, 9 times 25, those are both perfect squares, and in fact, 225 is a perfect square. 225 is 15 times 15, and so 225 is a perfect square, and 9t squared is a perfect square, and so there is a special factoring for that. 15 plus 3t times 15 minus 3t. All right, and you can verify if you'd like on your own that this factoring works. It's called the difference of two squares. Okay, now we can ask, could either of these factors equal 0? Well, yeah, they could. If 15 plus 3t equals 0, we can solve that for t by subtracting 15 from both sides and dividing by t. We get t equals -5. And if we set our other factor equal to 0, if we set 15 minus 3t equal to 0, well, we add 3t to both sides, divide by 3, and we get t equals +5. Okay, now these 2 points, they have a special name, right? These are called critical values of the function. Those are values that make the derivative g prime equal 0. We're going to have some other theorems about critical points, but those local maxima and those local minima, like those hilltops and those valleys that I drew a moment ago, those can only occur at critical points. And so in many, many problems, we're going to start by taking a derivative, setting equal to 0, and finding critical points. So now what this means is that there are only 2 values of t for which the derivative equals 0. And all other values of t, the derivative has to either be strictly positive or strictly negative. So if we think about all those possible values of t, I'm going to draw them just on a little like number line here. Say, all right, well, t equals 5 is up there, and t equals -5 is over here. And what that does is it divides all these other values of t into just 3 different intervals. The ones that are less than -5, the ones that are between -5 and 5, and the ones that are more than 5. We know that g prime at those 2 points is 0. And then all we need to do to finish this problem is figure out whether g prime is positive or negative on each one of these 3 intervals. And we can do that a couple ways. I think the easiest way for us, the way we've done the problem so far, is to plug in some test values here. So I'm going to pick a value in between -5 and 5, and we're going to pick it so that our work is easy. 0 is in between there. So what I want to do now is figure out what happens to g prime when we let t equal 0. Okay, well, let's see. We have a bunch of different ways we've written it. Maybe I'll just go to maybe this one right here. I'll just take this expression. And I'm going to say plug it in, but we actually don't even really care what the number is. All we care is whether it's positive or negative. So if I let t equal 0 in this expression, the numerator then would be 225, right, minus 0. So 225 up top. Down here, we let t equal 0, and we get 25 squared. So whatever that is, it's a positive number divided by a positive number. So we know now that the derivative, g prime, is positive when t equals 0, right? You don't have to know, it doesn't matter that it's 225 over 625. What matters is that it's positive. And so that tells us that we've actually identified one of the intervals for which g is increasing. So g is going to be increasing in between -5 and 5. We have 2 more intervals to test now. We need to know what happens when t is less than -5 and when it's more than 5. And again, we have some options. We can use any one of the different versions of our derivative that we have written here. So let's say t is greater than 5. Let's say t is 10, for example. What I'm going to do now is just like look through this factored form of my derivative and just ask myself, all right, are the different parts positive or negative? Like if I let t equal 10 here, I get 15 plus 30. Okay, that's positive. If I have 15 minus 3 times 10, oh, that's 15 minus 30. That's a negative quantity. And then down here in the denominator, we already decided the denominator is always positive. And so again, without even caring what the number is for the derivative, I can still reason that the derivative will be negative. G prime will be negative when t equals 10, because we'd have a positive times a negative divided by a positive, right, which is negative. So same reasoning for a factor that's less than -5. I'm going to choose maybe -10. So if I let t equal -10, okay, well, if t is -10, then 15 plus 3 times -10, that's going to be negative. And then if I plug in -10 here, I'd have 15 minus 3 times -10, so that's actually 15 plus 30. So that factor is positive, and then the denominator is positive. So just looking at my purple work here, I'd have a negative times a positive divided by a positive, so negative. So this little chart that I made down here, this is a really helpful tool. Just going to outline it here. It's called a sign chart, and it's just a number line. It's a number line that has a few things on it. First, I labeled up top that up top I'm keeping track of values of t, and then on the bottom, below the line, I'm keeping track of whether g prime is positive or negative. And I know that g prime equals 0 at my critical points, and then I chose 0 as a representative point in between -5 and 5. I could have picked 1, I could have picked 4, I could have picked pi. Doesn't really matter. They're all going to be the same. They're all either going to be positive or all be negative because we have a continuous function here. Okay, so back to the WebAssign problem. They asked us to find both increasing and decreasing intervals. I am going to go back to the screen share here in a moment, but I want to make sure that we read this correctly here. G prime is positive in between -5 and 5, right? But not including those 2 points. At those 2 points, the function is neither increasing nor decreasing. So increasing for values of x that are greater than -5 and less than 5. I'm just writing that as an inequality here because I think people are more familiar with that than interval notation. We'll put it in interval notation for WebAssign in a moment. Decreasing when x is less than -5 or x is greater than +5. All right, so back to WebAssign here. Okay, so the increasing interval, remember that was from -5 to 5 excluding. So in interval notation, we use the parentheses to indicate that we're not including an endpoint. So parentheses -5, comma 5. That means all the x values that are greater than -5 and less than +5. And then to do the decreasing interval, I actually have 2 different intervals here. And WebAssign can get a little bit picky about how you write these. I think if you separate them using commas, I don't know if it accepts it. Let's find out. So for x to be less than -5, we're actually going to write that as an inequality, or we're going to write it using interval notation involving infinity here. So infinity, there we go, there's my infinity symbol. When we go from -infinity to -5, but not include either one of those. Whoops. Anytime you use an infinite quantity in interval notation, you should be using an open interval with parentheses instead of a bracket. And I'm just curious whether it will accept this as two, whoops, -5, whether it will accept this as 2 different intervals separated by a comma. -pi, man, having a hard time doing what I'm saying here. There we go. So we're going to go from -infinity to -5, and then from 5 to +infinity. All right, I'm going to hit enter, see if it likes my answer. Leave it to on the bottom here. Okay, let's see if it likes it. Doesn't like the ones that we didn't enter. Oh, okay, cool. So it did, it accepted my answer as 2 different intervals separated by a comma. The other thing that you can do here is you can use the union symbol. You can't use the letter U. If I remember right, that was an issue that some students were having in the past. They like wanted to use the union and they didn't see the symbol, so they used a U, and WebAssign didn't like that. All right, so that's a pretty involved problem there. If you think about all the things that we did, we used quotient rule to find a derivative. We then had to combine like terms, do some simplifying, and then figure out when that derivative g prime was positive and when it was negative to understand when g was increasing or decreasing. Any other questions on that particular problem? What other problem should we look at from 4.1?
I did have a question on number 9 as well.
Yeah. All right, so number 9, again, I'll just do some general comments on it and then go to the whiteboard. So we're gonna have a lot of problems in calculus where we're interested in relative maxima and minima. So again, maxima are just high points on the graph relative to their neighbors, so little hilltops. Doesn't have to be the highest point for the whole function, just in the neighborhood. And the valleys, those are relative minima. That could be a sharp valley like a V or a U. And we're interested in those for a variety of reasons. If we have a function that models something in the real world, like maybe involving finance, we want to maximize revenue at a factory, or we want to minimize the amount of pollutants going into a body of water. If we have some function that's measuring something like that in real life, we are often interested in specifically those extreme values. And so it's a major emphasis in calculus here. We're going to have more than one way of finding these by the end of this chapter. And at the very end of the course, we're actually going to delve into a little bit of Calc 3. We'll do things that people don't do in Calc 1 or Calc 2 and look at functions of multiple variables and do a little bit of finding maxima and minima in 3 dimensions. It's really cool. We'll use some software to do it. And I think actually you'll find it easier than implicit differentiation. So we look forward to that in a few weeks. All right, so how do we find these things? Well, let me just copy the function down. Let's go over to the whiteboard here. So I have f of x equals x squared minus 8x. And hopefully you know a little bit about that function. You don't need to know exactly what it looks like, but hopefully you know, okay, that's a parabola. And parabolas, they're either upward or downward opening and are vaguely U-shaped. And so we should anticipate that there's probably either a local minimum or a local maximum, but not both necessarily for this particular one. Okay. All right, so here's the theory behind finding relative extrema using what we call the first derivative test. And it goes back actually to the last problem that we just looked at. If we imagine a smooth curve, there are, and yeah, I'll do a non-smooth curve after this, but if we imagine a smooth curve and we want to talk about relative extrema, okay, well, the curve that I drew is not this function f, but it does have a couple local maxima, right? So there's a local max right here, and then there's another one up here. And it has one local minimum. And together, we would say, all right, well, this function, at least on the interval that we've graphed, has 3 local extrema. And those mean extreme values, maxima and minima collectively. All right, so, well, what else do we notice about this graph here? Well, I mean, a number of things. One thing that I noticed is that at each one of these points, the graph has flattened out momentarily, right? If we drew a tangent line at that local maximum, it would be horizontal. Same thing for this local minimum. A tangent line there would be horizontal, right? And so at each one of these local extremum, we would expect that the derivative would equal 0 because the derivative gives us the slope of the tangent line. I'll say something else. I'll go beyond that. I noticed that the local maximum is precisely where the function switches from increasing to decreasing, right? The function is increasing on the interval all the way up to the local maximum, and then it switches to decreasing. And then it decreases for a while, it flattens out, and then it increases again, and then it decreases. And so what we're going to do to locate these local maxima and minima is see if we can figure out where the function switches between increasing and decreasing and increasing, knowing also that these points have to be points where the derivative equals 0. All right, so that's all just general background on finding extreme values. Let's now apply it to the function we have there. Maybe I'll leave this up for a couple more steps before I erase it. So we have f of x equals x squared minus 8x. First thing I'm going to do is take f prime, and thankfully they've given us a pretty straightforward function to do this with, so we're just starting on finding extreme values, but you can imagine harder problems that we have to use derivative rules to do this. Okay, so step one, I took the derivative f prime, and I'm going to set that equal to 0 now. So I want f prime of x to equal 0, and f prime of x is given by 2x minus 8. If I solve this equation, I will have found critical values or critical points for the function f. So solving 0 equals 2x minus 8, I'll add 8 to both sides. So 8 equals 2x, and divide both sides by 2. I have x equals 4, right? So there's a critical value. Critical values occur really in two different places. If we could find any point where the derivative was undefined, that would also be a critical value. The function could be switching between increasing and decreasing, and vice versa at that point. More typically, though, we're going to find it by setting it equal to 0. And thankfully, it's just a linear function here, but if we have a higher degree polynomial to start with, we might need to solve a quadratic to find those critical values. So all we know so far is that the function flattens out when x equals 4. And that could happen in a lot of ways. It could happen like this, right? If this is like x equals 4, it could be a downward opening parabola. I think you probably know it's not. Could look like that, right? Could be an upward opening parabola at x equals 4. Or it could do something totally different. It could like flatten out and then increase again. That could be x equals 4. So we don't really know between these three scenarios what's happening at x equals 4 yet. So what we're going to do is, similar to what I did in the last problem, make a little sign table for f prime of x. So again, sign table is just a linear graph, just a line. I'm going to plot any critical values on it. So I'll just pick a point and say, all right, well, that's x equals 4. And I know that f prime is 0 when x equals 4. Well, that critical value divides the number line into just two subintervals. X is less than 4 and x is greater than 4. And we want to know whether f prime is positive or negative on those two sides there. All right, well, I can pick any value less than 4, and it will be representative of all values less than 4. So why don't I pick an easy one? I'll pick maybe x equals 1. I'm going to write that up here. And if you're doing these problems on a quiz, like, it is nice, and again, for full credit, showing all your work, like I want you to actually try some value. So let me know what value you tested here. All right, well, what's f prime of 1? F prime of 1 is 2 times 1 minus 8, which is negative 6. Okay, so f prime is negative. If you just write a minus sign there, I'm fine with that. We've determined that f prime is negative for all values of x less than 4 on the basis of our math right here. So that means the function f is going to be decreasing all the way up until it hits x equals 4. All right, well, let me test another value. Let me test 10 maybe. I don't know. I can test whatever I want as long as it's bigger than 4. Well, what's f prime of 10? F prime of 10 is 2 times 10 minus 8. So it's 20 minus 8, which is 12. Okay, and importantly, this is a negative number, and this is a positive number. We know that if f prime is negative, then f is decreasing, and if f prime is positive, then f is increasing. And so the shape that we get then, we have a function that decreases, flattens, and then increases. And that tells us exactly what's happening now at x equals 4. It tells us that we're at a local minimum. So we have a local minimum at x equals 4. And I want to find out what that minimum is. I forget what the problem asked us. This tells us where it occurs. So all right, it's going to happen at x equals 4. But I also want to know what that minimum y value is. So I can find that just by plugging x equals 4 into our original equation. So what is f of 4? F of 4 is 4 squared, so 16, minus 8 times 4, so minus 32. So y equals, I think, negative 16. That's our ordered pair, 4 comma negative 16 is the local minimum. So if we had multiple critical values, we would then be looking for local maxima at points where the function changes between increasing and decreasing, equivalently where f prime changes from positive to negative. We don't have any for this function, so there are no local maxima for this particular function. Are there questions on this problem? I'll note, I think in section 4.2 and 4.3, there's another way that we can go from a critical value and figure out whether it's a maximum, a minimum, or neither. It's called the second derivative test. This is called the first derivative test, what we just did here. We found the first derivative, set it equal to 0, plotted those points on a number line, and then we tested what happened to f prime by plugging in other points here. By the end of the week, you'll have 2 or 3 different ways that are all pretty closely related to do the same thing. But in all these problems, if you're looking for a maximum or a minimum, you're always going to start by taking your function and differentiating, setting equal to 0 to find your critical values. Okay, other problems? Okay, well, these were both really good questions. I think that do a good job of transitioning from the end of chapter 3 with related rates into the beginning of chapter 4. Chapter 4 is all about applications of derivatives. I think, please don't hate me if I'm wrong on this, but I think you're going to find this chapter to be a little bit easier than chapter 3. And it's not because it's, the problems are easy, but they use the tools that you've already seen in chapter 3 for the most part. So you have to figure out, okay, what do I do with this derivative? But chapter 3 I think is hard because you're learning how to take derivatives for the first time. The more of them you do, the easier it becomes. I think I'm gonna stop recording now, but I'll just mention to folks who watch this later on, I may add another live session just to make sure that we're not getting too far behind on some of the chapter 3 topics. I might do an extra one tomorrow. If so, I'll put that in WebAssign.